All right, here's continuation of experimental and theoretical probability. Events are complementary if their probabilities add up to 1. This means that one of the events is certain to happen. Example 1. The probability of rain on Tuesday is 0.2. So as a percentage, that's 2 places to the right of the decimal place is 20%. What is the probability that it does not rain on Tuesday? So its complement is 0.8 or 80% chance. And if you want to do this algebraically, the probability of no rain equals 1 minus the probability that it will rain. So 1 minus 0.2 is 0.8. That's how you can use our complements. Example 2. A DJ randomly selects 2 of 8 ads to play before her show. 2 of the ads are by a local retailer. What is the probability that she will play both retailers' ads before her show? So step 1, we want to identify if this is a combination. So the order in which she plays the ads does not matter. So order does not matter. So we need to figure out the entire sample space. So there are 8, and you're going to choose 2. So 8, and you're choosing 2 ads. So let's figure out the sample space. So we've done this in a previous lesson. So 8 factorial goes in the numerator, and then the denominator will be 2 factorial, and then 8 minus 2 factorial is 6 factorial. And then we simplify the numerator down to 8 times 7 and then 6 factorial, and then expand the denominator 2 times 1 and then 6 factorial. The 6 factorials will cancel. We multiply across. 56 divided by 2 is 28. So there are 28 possible outcomes for our sample space of choosing 2 out of 8 ads. Step 3, find the number of favorable ads. So the favorable ads is the selection of the 2 retailer ads. So that means there is only one way to choose both retailer ads. So the probability of that happening is the probability of both retailer ads is the number of favorable outcomes, 1, out of the sample space of 28. Geometric probability is a form of theoretical probability determined by a ratio or a fraction of lengths, areas, or volumes. Area models are another way to organize and visualize theoretical probability. So let's recall some typical area formulas that may be helpful when we see our probability. So rectangle, the area of a rectangle is our length times our width. the area of a triangle is our height in the top, and then we have our base on the bottom. So the area of a triangle is 1/2 the base times the height. The last one is our circle. So we have the center of our circle out to our radius. The area of a circle is pi r squared. Example 4. The shaded area is vertically centered in the flag, and we want to find the probability. So what we have is a rectangle inside another rectangle. And we want to find out if we randomly select a point inside the flag in the shaded region. So we first need to figure out the area of the large rectangle. So the area here in the green. So the area of the green rectangle is going to be the length times the width. So 14 times 35 is 490. And then we have the area in the red, the smaller rectangle, and its length and width, so 2 times 35, we get 70. All right, now what we're going to do is answer part A. It says, if we randomly select a point inside the flag, so inside of here, what will be the probability that we land in that shaded region? So the favorable outcome is this area here out of the entire sample space of the green. So the probability of our red is the red area divided by the green area. So 70 divided by 490, which reduces to 1/7. Part B. A random point inside the flag is shaded above the region. So above the shaded region. So now we're talking this area right here. So we need to find the area of that part of the triangle, or triangle rectangle. So that length is 2 inside here. So then we have left 12 to split. So this is 6 here and 6 there. So the length and width would be 6 times 35, which is 210. Then we're going to go ahead and do our probability. So the probability above the shaded region so landing in the brown. So you're going to do the brown area over the green rectangle, the entire rectangle. So 210 divided by 490, and then we reduce that fraction. Example 5. 3 semicircles with diameters 2, 4, and 6 centimeters are arranged and shown in this figure. If a point inside the figure is chosen at random, what is the probability that the point is inside the shaded region? So inside the purple. So what we have to do is we have to find out what is the area of the entire circle. So that's going to be our sample space. And that is 1/2 of a circle. So let's talk about the area of the green is 1/2 pi r squared. And the radius of that circle is half the diameter, so 3 centimeters. So that'd be 1/2 pi times 3 squared. Which is 9 divided by 2 pi, or 4.5 pi. Then we need to find the area of this region here. So that semicircle has a radius of 2. So again, we're going to use the same formula, 1/2 pi r squared. So 1/2 pi times 2 squared. So 1/2 times 4 times pi is 2 pi. And then we have the smallest half circle. Same formula, 1/2 pi r squared. So 1/2 pi, and its radius is 1. So we get 1/2 pi. Now what we want to do is figure out this shaded area in the brown. And that is the favorable outcome. So we have to subtract out favorable, oops, I'm trying to write favorable here. So the favorable outcome is taking the green area, 4.5 pi, and subtracting out 2 pi and 1/2 pi. So 4.5 minus 2 minus 1/2 gives us 2 pi. So that is this area right in here. Now we're going to go ahead and answer the question. If a point falls inside of that brown region, what is the probability that the point is inside of it? So we do take the entire sample space. So the entire sample space is this green half circle, which was 4.5 pi. And then the favorable outcome, which is this green area, or green-brown area, of 2 pi. And then we simplify it. The pi's are going to cancel, so we're left with 2 divided by 4.5 pi, which is approximately 0.444.